Now that we've established the difference between net and total area, let's approximate net area or the definite interval using our left point approximation technique. We've already looked at how this works. You draw the rectangles based on the leftmost point. The only difference between this and when we learn total area is that we will consider all these rectangles below the x-axis as negative. Unfortunately, it's going to be a little bit easier because whenever the y value is negative, that will take care of the fact that it'll make this area negative. For example, this first rectangle has a y value of -3 down here, so it has a negative height, and therefore its negative area would be -3 times 0.5, which is -1.5. We can see it's going to be true for this rectangle as well. Then the rectangles become positive, and then the area of the last one will be negative, where we have a few in between that have a 0 area because they have a 0 height. Now the real question though is, without having to draw the function every time, is there a way of coming up with a formula, and a concise formula, that will give us an approximation every time? The answer is yes. So to determine the net area, plug in all of the x values into the function. Notice we're not taking the absolute value each time, we're just finding the y value of all of these individual rectangles, okay? And just like we did before with total area, if we find all the y values, all we have to do is add them up and multiply by the width of each rectangle, and that will give us an approximation of this area. Again, it's kind of like pulling out the width of each rectangle as a GCF, because that's what all of these have in common. If we add up all of the heights and multiply by that GCF, it will give us the total area of, the net area of all of these rectangles. So let's go ahead and just write out all of these y values. Now again, we're skipping the last x value too, because it's left point. For right point, you will skip the first value and include all the way up into the end. Again, as I've said before, for this particular interval, we're using 8 rectangles, right? But there's actually 9 x values, which makes sense. There's going to be one more point than there are rectangles. Now, why are we using 8 for right now? We're using 8 rectangles because since it goes from -2 to 2 and our interval is 4, 8 would make each width of a rectangle 0.5. If we tried to make it 9 or some odd number, it would be a weird width. But I'm going to show you what happens when we increase these number of rectangles. So again, if you haven't watched the video yet on total area, make sure you watch that first. It will kind of explain a little bit more why we're using these number of rectangles. So we get these 8 y values. We add them all up, we get -3.5. And if we multiply that by our GCF, which is the width of each rectangle, we get an approximation of -1.75. I'm going to use GeoGebra to allow you to look at what that looks like in this computer program. And in a second, we're going to increase those number of rectangles and see what happens. Now we're going to also look at the actual area, which is at -1.33. We can see that that's what happens when you add these three together, or that -4/3 figure we looked at when we compared net and total area. So the question is, how do we get this number, our left approximation, more accurate, where we're going to need to increase the number of rectangles? Now here's where I want to really be careful. I want to show you the summation notation for left point approximation. Now why do we use summation notation? It's because it's more concise. It just takes a lot less writing out. Notice all of these different y values we had to write out. Now, the reason we can use summation notation so easily is because the increment for each of these x values is the same. It goes up by 0.5 every time, or the width of each rectangle. Okay? And so, because of that, we can use summation notation, and we're adding a bunch of stuff up, right? We're adding all these y values up, so it makes sense that we would use summation notation. So it's going to be a little overwhelming at first, but I'm going to explain each of these components to you. So the first thing you should look at in summation notation is the summation sign. This indicates that you're adding a bunch of numbers up. Now for each summation notation, you have a counter, okay? You can either start at 0 or 1, depending on the application. For left point approximation, we're going to start at 0. I'm going to explain why. Your counter doesn't have to be I. Sometimes people use J, okay, but I becomes before J, so we're just going to use I equals 0 first. Now let's talk about these components inside our summation notation. So first of all, I want you to look at A. Okay, A is going to be our leftmost value. I'm going to have a key here I'm going to keep referencing. A is going to be your left interval boundary. Now in this case, we've been starting at -2. So here's your A over here. Okay, B is going to be your rightmost interval boundary. Since we're approximating the area from -2 to 2, A is going to be -2, B is going to be 2. Now the reason we start at I equals 0 is because if you plug in 0 into the summation equation, that will cancel out and you'll just have f of A. Okay, so notice how we started with f of A, f of -2. This is why we make I equals 0 for our first counter value. Now, what is change in x? Change in x is the width of each rectangle. So notice if you make I equal to 1, you'll be taking A and adding 1 times the change or the width of each rectangle. So it'll be A plus 1 times 0.5. Now A times 1 times 0.5 is 0.5, so A plus 0.5 will land you here, and f of that value will give you the height of the second rectangle. So the way summation works is you just keep popping along for each rectangle. Notice if I plug in 2 for I, it'll be A plus 2 times 0.5, and we will basically be going like this, adding the width of each rectangle twice. That y value happens to be 0, but if we make I 3, we can see we get the fourth rectangle, which actually has a particular height to it. So this is the formula for left approximation. Now the last thing I want to talk about is, the top of the summation, which is where you stop adding. Now n, let's go back to our key, is going to be represented by the number of shapes, in this case rectangles. Now since we're using 8 rectangles, we only want to go to 7. Now why is that? Well, if you start at 0 and go to 7, that's actually 8 total, okay? And so the last value up here for our summation notation, since we're using 8 rectangles, is going to be 7. Now if you plug in 7 here, basically what that means is you're starting with A and you're hopping 7 spaces over. If you hop 7 spaces over, you land right here. And that's because it's left point. You don't want to include that last point because that's your right point. And so that's why there is an n-1 for the summation notation. So if I put parentheses around this, what this represents is the height of all of my rectangles. Now notice, after you do all that, you multiply by the width of each rectangle, which is 0.5, and that gets you your approximated area for left point approximation of this function 1 minus x squared. Last thing I want to talk about is, plugging all of this stuff into the general formula. So we said the width of each rectangle is 0.5. We can plug that in. We're going to use 8 rectangles, so we're going to plug in 8 for n. We're starting at -2, so we're going to plug in -2 for A. And then the width of each rectangle is 0.5 for each. So each time we hop, each time we increase I, we're going 0.5 each time. And again, 7 times, when I is 7, it'd be 7 times 0.5, which will give you your last y value of 1.5. I know it's a lot, and that's why I'm breaking this down as much as I can. But once you plug in everything for all of your different variables, you can start to see a more concrete summation notation. So this would be pretty much the shortest way of notating this left point approximation with rectangles. Now here's what we're really getting at with Riemann sum approximations. what I'm going to do is take the slider and increase our number of rectangles. And what you're going to see is those rectangles get closer and closer to the curve of our function 1 minus x squared. Now I'm only going to go to 100 because at that point it starts to just blend in. But you can see also that as I get to 100, this number right here gets very close to our actual area, net area, between 1 minus x squared and the x-axis, which is negative 4/3 or negative 1.33. We can see that as we start with 8, we got negative 1.5. That's kind of a bit of a difference between the actual, but as we increase our number of rectangles, we get really, really close to the actual number. Now, how do we notate that? Well, we're going to use a limit. We're increasing the number of rectangles, and so the limit as the number of rectangles approaches infinity of our left point approximation, so as n gets bigger and bigger, is going to give us the actual signed area from a to b, or the definite integral of f of x from a to b. And again, when you see this symbol right here, it means definite integral. What you need to be thinking about is the signed area, or the net area from a to b. And if we go back and look at our graph again, this is exactly what we're talking about. Our a is -2, our b is 2 in this case. And our signed area would be adding these three areas up, considering these ones on the bottom negative. And so when we write it as a limit as the number of shapes approaches infinity, that will actually give us the actual signed area. It will give us this area right here if these number of rectangles were to be infinity, because they're going to basically just become the curve as we make them infinity. So that is Riemann sums in a nutshell. When you make the number of shapes infinity, you get that definite integral, you give the signed area. So the limit as the number of rectangles approaches infinity is equal to the definite integral, or the signed area. So I know that's a lot, but hopefully that gives you some clear understanding of left point approximation. Next, we're going to look at right point, midpoint, and trapezoidal, and see how those relate to the definite integral as we make those number of shapes infinity. If you have any other questions about this lesson, let me know.